Hello, everyone, and thank you so much for being here. My name is Roee, and I'm a postdoc at the Technion. Today, I'm going to tell you about our work learning to characterize matching experts, which is a joint work with Ofra, Amir, and Avigdor. Before I dive in, I want to tell you about the problem of schema matching. Schema matching is a key component in data integration with the main incentive of providing correspondences between data elements and specifically database attributes. By way of motivation, consider the following word cloud with the most common column headers extracted from thousands of web tables. As we can see, the frequent headers lack semantics and use extremely general terms. For example, a description which can address a customer, a store, a product, and so on. Historically, schema matching problems were considered semi-automated tasks in which a human expert is the final decision maker. Yet are all humans experts in the schema matching task? Obviously not. What makes a human an expert in the matching task? This is exactly what we want to learn in this paper. In this work, we look at human matchers that interact directly with the matching system. In what follows, a human matcher is required to match corresponding elements in the schemata, as shown here. Note that different from algorithmic matchers, a human matcher performs a sequential decision-making process, and thus each decision is annotated with the decision time and a self-reported confidence level. The first decision in this example involves the two city attributes, was taken fairly quick and accompanied with a full confidence level of 1. The second decision took a little bit longer and was taken with a lower confidence of 0.8. In the third decision, the human matcher decided to match the same attribute as before or the date to an additional attribute named PO time. Apparently, after this decision, the human matcher observed that order date is basically composed of two attributes, PO day and PO time, and decided to lower the former decision confidence to 0.5. The final decision in this matching is PO code and order number, which is made with a high confidence of 0.9. In this work, we define 4 dimensions that characterize a human expert. A matching expert should be precise, should be thorough, should be correlated, should be calibrated. And having all these expertise, this is what makes a matcher simply invincible. The first dimension is precision. Precise experts should match correctly more pairs than they match incorrectly. We use the precision measure accompanied with the threshold to account for precise human matchers. A threshold of 0.5, which we use in our experiments, dictates that a matcher is able to provide more correct correspondences than incorrect ones. The second dimension is thoroughness, simply because we didn't find the proper adjective for the recall measure. Recall accounts for the number of correctly identified element pairs out of all the number of correct pairs that exist in total. Using a 0.5 threshold, a thorough expert can provide matches that have more identified pairs than misidentified pairs. The first two used well-known precision and recall measures, which are basically accuracy measures. We now look at the cognitive ability of a human matcher by basically quantifying their ability to tell us what they know and don't know. Correlated experts should be more confident when correct when incorrect. We use for this property the well-known metacognition measure of resolution, which basically accounts for the correlation between the reported confidence and the actual success. In these measures, we use the population to set the threshold, and in addition, we require our human matcher to have a statistically significant correlation. The second cognitive measure is calibration. And here we look at the difference between the reported confidence and the actual success. Here we also use the population, and note that here the sign of the measure is very important to know whether the human matcher is overconfident or underconfident. We now move to the task of matching expert identification, or MEXI for short. We position this problem as a multi-class, multi-label classification problem for which each class corresponds to a different expertise type. For our human matcher, we use two components for representation. The first is a decision history, as we saw in the example before, and the second is a movement map, which actually tells us where the human visited on the screen while performing the matching task. We begin with our human matcher, out of which we obtain these two aforementioned components. Using the decision history, we first use aggregated features such as average confidence and average decision times for the human matcher. Additionally, we perform a sequential learning phase to capture the decision-making process. Specifically, we use the sequence of decision times, the sequence of reported confidence levels, and the sequence of agreement with the other human matchers on the specific pair. Using an LSTM, we extract sequential features for which we train 4 different models, one for each expertise type, and we learn them conjointly in a late fusion manner. Finally, we use a set of matching predictors over the matching outcome to extract task-oriented features. Using the movement map, we first also extract aggregated features based mainly on the literature in the HCI community. In addition, we look at 4 interactions with the mousepad, namely right and left clicks, scrolling, and moving, and offer a novel use of deep learning to extract spatial features using CNNs. Here we also train 4 different models, one for each expertise type. Using all these models, we represent our human matchers, and following Reed et al., we train a multi-label classifier by basically training 4 different binary classifiers. In our empirical evaluation, we examine 3 main properties. First, we want to see whether our methodology performs better than state-of-the-art in identifying matching experts. Secondly, we wanted to see whether our model, which was trained on one domain, can be beneficial for a different domain. And finally, we wanted to see whether our matching experts, when we identify them by our method, can actually perform better in the matching task itself. Our human matching dataset contains more than 7,000 matching decisions by more than 140 human matchers performing 2 different tasks, the one of schema matching, and the second one is the ontology alignment task, which we use to show the generalizability ability of our model. Before we dive into the results, let's take a look at our participants. Our participants are science and engineering students that study database systems course. Each bar in this plot represents an expertise dimension. The darkest shade represents the matchers that are expert in all the 4 types. Above these, we see experts that are experts in 2 and 1 additional type, and the lightest shade on the top of each bar represent the proportion of experts that are expert in this type only. 53% of human matchers are precise, and only 15% are thorough. When looking solely at underconfident matchers, we observe a much higher performance of 84% precise matchers, 40% thorough matchers, and 80% calibrated. Finally, 5% of these matchers could simply snap their fingers, they would all cease to exist. I call that mercy. We compare the accuracy of our method to the baselines by expertise type. And in addition, we use a multi-label accuracy, which accounts for the completability of the model. We examine 3 variations of our model, a vanilla maxi, an enriched version, which bootstraps virtual submatchers, which are 50 consecutive decisions of matchers, and an additional variation that yielded slightly lower results. As we observe, our model is able to identify matching experts better than the examined baselines. In addition to the matchers that perform the schema matching task, we also experimented with an additional set of matchers aiming to solve an ontology alignment task. As you can see, Maxi performs well also for the ontology aligners, for which we actually use the model that was trained for schema matchers. And this serves as a proof of concept that a trained Maxi can achieve high quality results also for a new domain. Finally, we wanted to see whether the final matching outcome with and without identifying matching experts. For this analysis, we characterized a matching expert after 30 decisions and then decided whether to leave their scores or not. As you can see, our identified matches perform much better and improve, for example, the final precision by 42% and the final recall level by 90%. To sum, in this work, we offer a novel framework to identify and characterize human matches that uses a novel set of features. Our empirical analysis shows that our model can identify human experts better than common methods in human in the loop, is able to generalize beyond a single domain, and improve the matching outcome. Thank you very much. And if you have any questions, feel free to contact me. Bye-bye.